welcome to Chapter 7, Simple Connections. Connections of structural steel members are important. An inadequate connection can mean a weak link in structure, which has been the cause of many construction failures. Modern steel structures are connected by welding or bolting, or the combination of both. Before, it was welding and riveting, but in 1951, the bolting was authorized as substitute for riveting. Bolting became popular and riveting became obsolete. So here's how a rivet looks like. So now let's proceed to bolted connections. We want to design the bolted shear connections so that the factor design strength is greater than or equal to the factored load. So we need to examine the various possible failure modes and calculate the corresponding design strengths. So these possible failure modes are shear failure of the bolts, failure of member being connected due to fracture, edge tearing or fracture of the connected plate, tearing or fracture of the connected plate between two bolt holes, and excessive bearing deformation at the bolt hole. And now for shear failure of bolts. The figure shows that bolts can be in single shear or double shear. When the bolt is in double shear, two cross-sections are effective in resisting the load. The bolt in double shear will have the twice shear strength of a bolt in a single shear. Now we can write the formula for the average shearing stress in the bolt as FV is equal to P over A. Or we can also write P over pi d squared over 4, where P is the load acting on the bolt and A is the cross-sectional area of the bolt. Now let's move on to the bearing failure of the connected part due to bearing from bolt holes. The hole is slightly larger than the fastener and the fastener is loosely placed in hole. Contact between the fastener and the connected part over approximately half the circumference of the fastener. As such, the stress will be highest at the radial contact point A. However, the average stress can be calculated as the applied force divided by the projected area of contact. So this can be written as average bearing stress F sub P is equal to P over dBT, where P is the force applied to the fastener and dt is the area. A possible failure mode resulting from excessive bearing close to the edge of the connected element is shear tear out, as shown in the picture. This type of shear tear out can also occur between two holes in the direction of the bearing load. To prevent excessive deformation of the hole, an upper limit is placed on the bearing load. This upper limit is proportional to the fracture stress times the projected bearing area. Or you can write R sub n is equal to C times Fu times the bearing area. The C is a constant. Now, if the deformation is not a concern, you can write C is equal to 3. But if deformation is a concern, then you can have constant is equal to 2.4. This corresponds to a deformation of 0.25 inch. Finally, the equation for the bearing strength of a single bolt is Phi times R sub n, where Phi is equal to 0.75 and R sub n is equal to 1.2 LCTFU less than 2.4 dBTFU. Your LC is the clear distance in the load direction from the edge of the bolt hole to the edge of the adjacent hole, or to the edge of the material. This relationship can be simplified as 1.2 LCTFU is equal to 2.4 dBTFU, therefore having LC is equal to 2D. Now, if your LC is less than 2D, your RN is equal to 1.2 LCTFU. But if your LC is greater than 2 dB, your Rn is equal to 1.4 dBTFU. Now we have design provisions for bolted shear connections. In a simple connection, all bolts share the load equally. The shear strength of all bolts is equal to the shear strength of one bolt times the number of bolts, and the bolts are subjected to shear and the connecting parts are subjected to bearing stresses. Now for the AISC design provisions, it indicates that the minimum distance or distances between the centers of bolt holes is 2 2/3 dB, but a distance of 3 dB is preferred. Now for AISC specification J3.4, it indicates that the minimum edge distance or the LE from the center of the bolt to the edge of the connected part is given in table J3.4 on page 16.1 to 61. This table specifies minimum edge distances for sheared edges, edges of roll shapes, and gas cut edges. Now for J3.5, it indicates that the maximum edge distance for bolt holes is 12 times the thickness of the connected part. The maximum spacing for bolt holes is 24 times the thickness of the thinner part. And the design bearing strengths are given for different edge distances. So we have 1.25 inch and 2 inches. Different FU, so we have 58 and 65 psi. And different bolt diameters from 5/8 to 1 1/2 inches. So for our example, here we have to calculate and check the design strength of the connection shown, and is the connection adequate for carrying the factored load of 65 kips. So here in our figure, we can see the dimensions of 3/8 inch and 5/1/2 inch of an A36 steel. And we have a factored load of 65 kips, and the diameter of our bolts is 0.75 inches. And also for the distance between the center of the bolt hole to the edge of the plate is 1.25 inches, and the distance or the spacing from the center to center of our bolts is equal to 2.5 inches. But before we're going to solve this problem, first we have to discuss the flowchart. So here are the steps for solving the bolted shear connection. Step 1, check the shear strength of bolts. So use the formula shear strength of one bolt is equal to Phi times F sub n times AB. For the shear strength of the whole connection, just multiply it by the number of bolts. For step 2, check for the minimum edge distance and spacing requirements. So for the minimum edge distance, just see table J3.4 of the AISC specification manual and compare it with your distance shown in the figure. And for the minimum spacing, use the formula 2.67 or 2 2/3 dB, or use the preferred spacing of 3.0 dB. So just compare the value and check if it is satisfied. For step 3, check for the bearing strength at bolt holes. So there are 2 bolt holes. We have the bolt holes in the connected part and the bolt holes in your gusset plate. So under the bearing strength for bolt holes, so check for your LC or your clear distance. So we have LC is equal to LE minus H/2. So LE is your distance from your edge to the center of your bolt, and next we'll be solving for Phi times R sub n, which is equal to 0.75 times 1.2 LCTFU. Then check for another Phi times R sub n, or your upper limit, which is equal to 0.75 times 2.4 dBTFU. Then compare the values and choose the lesser value for your Phi times R sub n. So just repeat this process in the bearing strength at bolt holes in the connected part to the bearing strength at bolt holes in the gusset plate. And the last one would be your conclusion. So just show your connection strengths, shear strength, bearing strength of your plate, and bearing strength of your gusset. Then conclude if the connection is adequate or not. Now let's go back to the problem, which is calculate and check the design strength of the connection and check if the connection is adequate for carrying the factored load of 65 kips. So let us follow the steps. We have step 1, shear strength of bolts. So shear strength is equal to Phi times F sub n times AB. So our F sub n is equal to 48. So this is from the AISC manual for A36 type of steel, and our diameter is 0.75. So solving, we have 15.9 kips per bolt. So for the whole connection shear strength, just multiply it by the number of your bolts, which is 4. So 15.9 times 4 is equal to 63.6 kips. Then step 2, check for the minimum edge distance and spacing requirements. So as per AISC manual, table J 3.4, the minimum edge distance is equal to 1 inch. And our given distance is equal to 1.25. So since our given distance is greater than the minimum, therefore, the minimum edge distance requirements are satisfied. Now, for the spacing, we have 2 and 2/3 D or 2.67 times D, which is 0.75, we have 2.0 inch. Now, for the preferred spacing, we have 3.0 times 0.75, so we get 2.25 inch. And our given spacing in the figure is 2.5 inches, which is greater than the preferred spacing of 2.25 inch. Therefore, the spacing requirements are satisfied. Now for step 3, check for the bearing strength at bolt holes. So again, we have to check the bearing strength at the bolt holes in the connected part and in the gusset plate. So first, check for the bolt holes in the connected part. So as you can see, we have two types of bolts. So bolts at the edges and bolts at the other side. So for the bolts at the edges, we have our LC clear distance, which is equal to LE minus H over 2. So LE is your distance from the edge to the center of your bolt. So we have from the given 1.25, then our hole diameter, which is equal to D plus 1 over 16. So solving this, we get 0.844 inch. Then for our Phi times R sub n is equal to 0.75 times 1.2 LCTFU. So for our T, it is given, which is 1/2 or 0.5. And our LC, we have already solved it, which is equal to 0.844. And for our FU, it is 58. So FU is given from the manual. So we solve this, we get 22.02 kips. Now for the upper limit, we have 0.75 times 2.4 D times T times FU. Then we have our D, which is equal to 0.75. Our thickness again is 0.5, and our FU again is 58. So we solve this, we have 39.15 kips. So comparing the values 22.02 and 39.15, so 22.02 is less than, so we get our Phi times R sub n, which is equal to 22.02 kips at edge holes. Now for the other holes, we solve for our clear distance with the formula LC, which is equal to S minus H. So in the figure, our given S, or the spacing from the center to center of our bolt holes, is equal to 2.5. So substitute the value into LC is equal to 2.5 minus D plus 1 over 16. So again, our D is 0.75. So we get 1.688 inches. Then go back to the process Phi times R sub n for the lower limit and the upper limit. So we get the values 44.05 and 39.15. So choose the lesser value, which is 39.15 kips. So therefore, our Phi times R sub n is 39.15 kips at other holes. So therefore, the bearing strength at bolt holes is equal to 2 times 22.02 plus 2 times 39.15. So total of 122.34 kips. Now for the bearing strength at bolt holes in the gusset plate, just repeat the process and substitute the corresponding values. So our V times R sub n for the edge holes, we get 16.52 kips, and for the other holes we get 29.36 kips. So multiply it by 2, then add everything. So we have 2 times 16.52 plus 2 times 29.36, then we get 91.76 kips. So the bearing strength of the connection is the smaller of the bearing strength, so we have 91.76. Now for our summary, in the connection strengths, we have the shear strength, which is equal to 63.3 kips, the bearing strength for the plate, which is equal to 122.34 kips, and the bearing strength in the gusset plate, which is equal to 91.76 kips. So therefore our connection strength is greater than the applied factored load, which is equal to 65 kips. So therefore our connection is adequate or okay.
Slip critical and bearing type connection. A slip critical connection is one in which no slippage is permitted. That is, the friction force must not be exceeded. In a bearing type connection, slippage is acceptable, and shear and bearing actually occur. In some types of structures, notably bridges, the load on connections can undergo many cycles of reversals. In such cases, fatigue of the fasteners can become critical if the connection is allowed to slip with each reversal, and a slip critical connection is advisable. In most structures, however, slip is perfectly acceptable, and a bearing type connection is adequate. Flowcharts or steps. First is for the investigation. First, we have to check for the shear strength. Check for slip critical strength. Check for bearing strength. Check for tension and gross area. Check for tension and net area. Check for block shear strength. And lastly, multiply with the corresponding LRFD and AST coefficients to get the results required. Next is for the design. First, determine if the bolts are in double shear or single shear. Assume that shear controls and check bearing strength. Solve the factored load PU and determine the number of bolts needed. Determine strength to be carried by each bolt with the corresponding distances, whether edge or inner. Obtain the strength of the connection based on shear and bearing by adding the minimum strengths of each bolt location. As discussed earlier, the resistance to slip will be a function of the coefficient of static friction and the normal force between the connected parts. This relationship is reflected in the provisions of the AISC specification. The nominal slip resistance of a bolt is given by Rn, which is equal to mu du hf tb ns, where mu is the mean slip coefficient, or the coefficient of static friction. For class A, we have 0.30. For class B, we have 0.50. For class C, we have 0.40. And for standard hole, we have 1. du is the ratio of mean actual board pretension to the minimum pretension. This can be taken as 1.13 unless other factor can be justified. Tb is the minimum fastener tension from AISC table J3.1. Ns is the number of slip planes for the shear planes. Hf is the filler factor. The filler factor HF accounts for the presence of filler plates, which are sometimes added to connections to bring elements into alignment. This can occur, for example, when members of different depths are spliced. The HF will be equal to 1 when bolts are added to distribute loads in the filler and one filler is used, and 0.85 when the bolt have not been added to distribute loads in the filler and 2 or more fillers are used. Investigation example. The connection shown in figure 7.13a uses 3/4-inch diameter group A bolts to the threads on the shear planes. No slip is permitted. Both the tension and the gusset plate are of A36 steel. Determine the strength of the connection. Both the design strength LRFD and the allowable strength ASD will be computed. For efficiency, the nominal strength for each limit state will be computed before specializing the solution of the LRFD and the ASD. Solution. First, we have to check for the shear strength. Shear strength for one bolt, first we have to solve for the area of the bolt, which is equal to pi 3/4 squared over 4, equal to 0.4418 inches squared. Now we will solve for Rn, which is equal to F and B AB, and substituting the value, we get 23.86 kips per bolt. Now, we will check for the slip critical strength. Because no slippage is permitted, this connection is classified as slip critical. The minimum bolt tension TB is equal to 28 kips. From the formula presented, Rn is equal to mu, du, hf, tb, ns, and hf. And substituting the value, we get 9.492 kips per bolt. For 4 bolts, we simply multiply it by 4 and we get 37.97 kips. Now we will check for the bearing strength. Since both edge distances are the same and the gusset plate is thinner than the tension member, the gusset plate thickness of 3/8 inch will be used. For bearing strength computation, use a hole diameter h, which is equal to d plus 1/16, and substituting the value, we get 13/16 inch. For the holes nearest the edge of the gusset plate, we'll first solve the clear spacing, which is equal to the edge distance to center of the hole minus the hole diameter over 2, and substituting the value, we get 1.094 inch. We will now solve for Rn, which is equal to 1.2 LC TFU, and substituting the value, we get 28.55 kips. We will solve now for the upper limit, which is equal to 2.4 DTFU, and substituting the value, we get 39.15 kips, which is greater than 28.55 kips. We will now use Rn, which is 28.55 kips for this bolt. For the other holes, LC is equal to S minus H, and substituting the value, we get 2.188 inch. We will now solve for Rn, which is equal to 1.2 LC TFU, and again substituting the value, we get 57.11 kips. We will now solve for the upper limit, which is equal to 2.4 DTF, and again substituting the value, we get 39.15 kips, which is lesser than 57.11 kips. Use Rn, which is equal to 39.15 kips for this bolt. For 4 bolts, since the upper limit is lesser than the Rn, we will use the Rn that we have computed for the shear strength, and we will just multiply it by 4, and we get 95.44 kips. Now we will check for tension on gross area. The nominal strength Pn is equal to Fy times Ag. And substituting the value, we get 108 kips. And now we'll check for tension and net area. All elements of the cross-section are connected, so shear log is not a factor, and AE is equal to AN. For the whole diameter, H, which is equal to D plus 1 over 8, substituting the value, we get 7 over 8 inch. The nominal strength, Pn, is equal to Fu times Ae, which is also equal to Fa times Wg minus summation of H. And substituting the value, we get 123.3 kips. Now, we will check for the block shear strength. Block shear strength. The failure block for the gusset plate has the same dimensions as the block for the tension member except for the thickness. The gusset plate, which is a thinner element, will control. There are two shear failure planes. Now we will solve for IGV, which is equal to 2 failure planes times 3 over 8 times 3 plus 1.5, and we get 3.375 inches squared. Since there are 1.5 hole diameters per horizontal line of bolts, A and B is equal to 2 times 3 over 8 times 3 plus 1.5 minus 1.5 times 7 over 8, which is equal to 2.391 inches squared. For tension area, A and T is equal to 3 over 8 times 3 minus 7 over 8, which is equal to 0.7969 inches squared. Since the block shear will occur in the gusset plate, UBS is equal to 1. Now we will solve for Rn, which is equal to 0.6 times Fu times ANB plus UBS Fu ANT. And substituting the value, we get 129.4 kips. Now we will solve for the upper limit, which is equal to 0.6 Fy ANB plus UBS Fu ANT. And substituting the value, we get 119.1 kips. The nominal block shear strength is therefore 119.1 kips. Now we will multiply with the corresponding LRFD coefficients. First is the bolt shear or the bearing strength. P is equal to 0.75 times 95.44. It is equal to 71.6 kips. For the slip critical strength, P is 1 times 41.96. We get 42 kips. For the tension and gross area, P is 0.90 times 108, we get 97.2 kips. And for tension and net area, P is 0.75 times 123.3, we get 92.5 kips. And for block shear strength, P is 0.75 times 119.1, we get 89.3 kips. Of all the limit states investigated, the strength responding to slip is the smallest. Therefore, design strength is 42 kips. Now we will multiply with the AST coefficients denoted as omega. For bolt shear or bearing strength, we will simply divide the Rn with the omega. Rn is 95.44 over 2, it is equal to 47.7 kips. For the slip critical strength, it is equal to 41.96 over 1.5, is equal to 28 kips. And for the tension and gross area, 108 over 1.67 is equal to 64.7 kips. And for the tension and net area, 123.3 over 2 is equal to 61.7 kips. And for block shear strength, we have 119.1 over 2, which is equal to 59.6 kips. Of all the limit states investigated, the strength corresponding to slip is the smallest. Therefore, the allowable strength is 28 kips. Design example. A 5/8 inch thick tension member is connected to two 1/4 inch splice plates. as shown in the figure 7.14. The loads shown are service loads. A 36 steel and a 5/8-inch diameter Group A bolts will be used. If slip is permissible, how many bolts are required? Each bolt center line shown represents a row of bolts in the direction of the width of the plates. Now we will solve for factored load PU and determine the number of bolts needed. Assume that shear controls and then check bearing. The required strength of the connection is PU is equal to 1.2 dead load plus 1.6 live load, and substituting the value we get 76 kips. Strength of each bolt from manual is equal to 24.9 kips per bolt. The number of bolts required is equal to required strength over strength per bolt, which is equal to 76 over 24.9. The number of bolts required is equal to 3.05 bolts, and try 4 bolts, 2 per line, 1 each side of the splice. Now we will determine the strength to be carried by each bolt with the corresponding distances with the edge or inner. The bearing force on the 5/8-inch thick tension member will be twice as large as the bearing force on each of the 1/4-inch splice plates, because the total load on the splice plates is the same as the total load in tension member. For the splice plates to be critical, the total splice plate thickness must be less than the thickness of the tension member, and it is. For the inner holes and a spacing of 3 inches, PRN is equal to 65.3 T. T there is the 2 splice plates, and substituting the value we get 32.7 kips per bolt. For the holes nearest the edge of the plate, we'll conservatively use an edge distance of 1 1/4 inch to find the bearing strength from manual. PRN is equal to 47.3 T, and substituting the value, we get 23.7 kips per bolt. Now, we will obtain the strength of the connection based on shear and bearing by adding the minimum strengths of each bolt rotation. To obtain the strength of the connection based on shear and bearing, we consider the total strength of the connection to be the sum of the minimum strengths at each bolt rotation. Thus, PRN is equal to 2 times edge bolt strength plus 2 times inner bolt strength. So, 2 times 23.7 plus 2 times 24.9, we get 97.2, which is greater than 76 kips. Solution for ASD. Solve for factored load PU and determine the number of bolts needed. Assume that shear controls and then check bearing. The required strength of the connection is PU is equal to D plus L, or the dead load plus live load, which is equal to 55 kips. Strength of each bolt from manual is 16.6 kips per bolt. The number of bolts needed is equal to required strength over the strength per bolt, which is equal to 55 over 16.6. The number of bolts required is 3.31 bolts. Try 4 bolts, 2 per line, on each side of the splice.
Determine the strength to be carried by each bolt with the corresponding distances, whether edge or inner. The bearing force in a 5/8-inch thick tension member will be twice as large as the bearing force on each side of the 1/4-inch splice plates, because the total load on the splice plates is the same as the load of the tension member, and the total splice plate thickness is less than that of the tension member. The bearing on the splice plates controls. For the inner holes in spacing of 3 inches, Rn divided by the safety factor is equal to 43.5 T, which is equal to 43.5 times 1/4 plus 1/4, which is equal to 21.8 kips per volt. For the holes nearest the edge of the plate, we will conservatively use an edge distance of 1 and 1/4 inches to find the bearing strength from the manual. Rn divided by the safety factor, which is equal to 31.5 T, which is equal to 31.5 times 1/4 plus 1/4 is equal to 15.8 kips per bolt. Obtain the strength of the connection based on shear and bearing by adding the minimum strength at each bolt location. To obtain the strength, Rn divided by the safety factor, which is equal to 2 times the edge bolt strength plus 2 times the inner bolt strength, which is equal to 2 times 15.8 plus 2 times 21.8, which is equal to 75.2 kips, which is greater than the 55 kips. Use 4 bolts, 2 per line, 1 each side of the splice. A total of 8 bolts will be required for the connection.
Good afternoon everyone. Today we're going to discuss about the high strength bolts in tension. When a tensile load is applied to a bolt with no initial tension, the tensile force in the bolt is equal to the applied load. If the bolt is pre-tensioned, however, a large part of the applied load is used to relieve the compression or clamping forces on the connected parts. Figure 7.24 shows a hanger connection consisting of a structural T-shape bolted to the bottom flange of a W-shape and subjected to a tensile load. A single bolt and a portion of the connected parts will be isolated and examined both before and after loading. Before loading, all forces are internal, and a free body diagram of the assembly is as shown in figure 7.25a. For simplicity, all forces will be assumed to be symmetrical with respect to the axis of the bolt, and any eccentricity will be neglected. If the connected parts are considered as separate free bodies, the forces consist of the bolt tension T sub O and the normal clamping force N sub O, shown here as uniformly distributed. Equilibrium requires that T sub O equals to N sub O. When the external tensile load is applied, the forces on the assembly are as shown in figure 7.25b, with F representing the total tensile force applied to one bolt. Figure 7.25c shows the forces acting on a free body diagram of the segment of the structural T-flange and the corresponding segment of the bolt. Summing forces in the direction of the bolt axis gives T is equal to F plus N. Application of force F will increase the bolt tension and cause it to elongate by an amount elongation B. Compression in the flange of the structural T will be reduced, resulting in a distortion elongation FL. In the same sense, an amount as elongation B. A relationship between the applied force and the change in bolt tension can be approximated as follows. From elementary mechanics of materials, the axial deformation of an axially loaded uniform member is elongation is equal to PL divided by AE, or solving for P is equal to AE times the elongation over the length, where P is equals the applied axial force, L is equal to original undeformed length and E is the cross-sectional area, and E is the modulus of velocity. The change in bolt force corresponding to a given axial displacement therefore is T is equal to AE times the displacement over the length, where the subscript indicates a property or dimension of the bolt. Application of equation 7.4 to the compression flange requires a somewhat more liberal interpretation of the load distribution in that N must be treated as if it were uniformly applied over a surface area. The change in the force N is then obtained. N is equal to surface area times the E times the displacement over the length. Where LFL is the flange thickness, as long as the connected parts remain in contact, the bolt deformation and the flange deformation will be equal. Because elasticity of the flange approximately equals to the elasticity of the bolt, and area of the flange is much larger than area of the bolt, and therefore the ratio of T to N is in the range of 0.05 to 0.1. Consequently, T will be no greater than 0.1 N, or equivalently, maximum T divided by N is equal to 0.1, demonstrating that most of the applied load is devoted to relieving the compression of the connected parts. To estimate the magnitude of the load required, damping effect and cause the parts to separate, consider the free body diagram in figure 7.26. When the parts have separated, T is equal to F, for T sub O plus T is equal to F. At the point of impending separation, the bolt elongation and plate decompression are the same, and T is equal to AB times elasticity times the H deformation over the length is equal to AB times elasticity times the deformation of the flange over the length of the bolt. Where elongation of the flange is the elongation corresponding to the release of the initial compression force N sub O. From equation 7.3, elongation of the flange is equal to the initial compression force times the thickness of the flange divided by the area of the flange times the elasticity. Substituting this expression for the elongation of flange in the equation 7.8 yields, we obtained T is equal to 0.1 T sub O. From equation 7.7, T sub O plus 0.1 T sub O is equal to F, or F is equal to 1.1 T sub O. Next is the prying action. The additional tension is called a prying force and is illustrated in figure 7.27, which shows the forces on a free body of the hanger. Before the external load is applied, the normal compressive force N sub O is centered on the bolt. As the load is applied, if the flange is flexible enough to deform as shown, the compressive forces will migrate toward the edges of the flange. This redistribution will change the relationship between all forces, and the bolt tension will increase from B sub O to B. If the connected parts are sufficiently rigid, however, the shifting of the forces will not occur, and there will be no prying action. The maximum value of the prying force Q will be reached when only the corners of the flange remain in contact with the other connected part. The corresponding bolt force, including the effects of prying, is B sub C. Figure 7.27 shows before and after external load and the maximum prying force. The method used is based on the model shown in figure 7.28 All forces are for one fastener. Thus, T is the external tension force applied to one bolt. Q is the prime force corresponding to one bolt. And BC is the total bolt force. The prime force has shifted to the tip of the flange and is at its maximum value. From the summation of moments at B to B in figure 7.28b, T times B minus M sub A to A is equal to QA. From figure 7.28c, M sub B to B is equal to Q times A. Finally, equilibrium of forces requires that BC is equal to T plus Q. These three equilibrium equations can be combined to obtain a single equation for the total bolt force, which includes the effects of prying action. We first define the variable alpha as the ratio of the moment per unit length along the bolt line to the moment per unit length at the base of the stem. For the bolt line, the length is a net length, so alpha is equal to moment from B to B divided by displacement times the moment A to A, where P is the length of the flange tributary to one bolt not to exceed 2 times the D. D prime is the diameter of the bolt hole, and the elongation is equal to 1 minus D prime over the P, or the net area at bolt line divided by gross area at stem face. The numerical evaluation of alpha will require the use of another equation, which we develop shortly. With this notation, we can combine the three equilibrium equations 7.9 through 7.11 to obtain the total bolt force BC. BC is equal to T times 1 plus elongation times alpha divided by 1 plus elongation times alpha times B over A. At this level of loading, deformations are so large that the resultant of tensile stresses in the bolt does not coincide with the axis of the bolt. Consequently, the bolt force predicted by equation 7.13 is conservative and does not quite agree with the test results. Much better agreement is obtained if the force BC is shifted toward the stem of the T by an amount D over 2, where is the bolt diameter. The modified values of B and E are therefore defined as B prime is equal to B minus D over 2 and E prime is equal to A plus D over 2. The three equilibrium equations 7.9 through 7.11 can also be combined into a single equation for the required flange thickness. From equation 7.9 and 7.10, we can write TB prime minus M sub A to A is equal to M sub B to B, where B prime has been substituted for B from equation 7.12. TB prime minus M sub A to A is equal to elongation times alpha times M sub A to A, where M sub A to A is equal to TB prime over 1 plus elongation times alpha. For LRFD, let M sub A to A is equal to design strength is equal to P times TF squared times Fy over 4, where Phi sub B is equal to 0.90. Substituting into equation 7.7, then we get Phi times P times TF squared times Fy over 4 is equal to TB prime over 1 plus elongation times alpha, where TF is equal to square root of 4 TB prime divided by Phi times P times Fy times 1 plus elongation times alpha, where T is the factored load per bolt. If the ultimate stress Fu is substituted for the yield stress Fy, required TF is equal to square root of 4 TB prime divided by phi sub b times p times fu times 1 plus elongation times alpha. For A is D, when we substitute fu for fy, we get m sub e to a is equal to allowable strength, mp over omega b is equal to 1 over omega times the p times the tf squared times fu over 4. Required tf is equal to omega times 4 times tb prime over p fu times 1 plus alpha times elongation, where omega sub b is equal to 1.67 and T is the applied service load per volt. If the actual flange thickness is different from the required value, the actual values of alpha and BC will be different from those previously calculated. If the actual bolt force, which includes the prying force Q, is desired, alpha will need be recomputed as follows. First, combine equation 7.9 and 7.10 using B prime instead of B. M sub B to B is equal to TB prime minus M sub A to A. From equation 7.12, alpha is equal to M sub B to B over elongation times M sub A to A is equal to TB prime divided by M sub A to A minus 1 divided by elongation. Subject to the limits, alpha is greater than or equal to 0 but less than or equal to 1. For LRFD, set M sub A to A is equal to phi times M sub B is equal to phi sub B times P times TF squared FU over 4. Then alpha is equal to 1 over elongation times 4 TB prime divided by phi times P times TF squared FU minus 1, where alpha is greater than or equal to 0 but less than or equal to 1. Where TF is the actual flange thickness, the total bolt force can be found from equation 7.14. For A is D, set M sub A to A equal to the allowable moment. M sub A to A is equal to 1 over omega times P times TF squared FU over 4. Then alpha is equal to 1 over elongation times omega 4 TB prime divided by P times TF squared FU minus 1. So let's take up some example. An 8-inch long WT 10.5 by 66 is attached to the bottom flange of a beam as shown in figure 7.29. This hanger must support a service dead load of 20 kips and a service live load of 60 kips. Determine the number of 7 over 8 inch diameter Group A bolts required and investigate the adequacy of the T. A992 steel is used. Compute the constants that are based on the geometry of the connection. B is equal to 5.5 minus 0.65. Divide 2 is equal to 2.425 inches. A is equal to 12.4 minus 5.5. Divide 2 is equal to 3.45. Since 1.25b is equal to 1.25 times 2.425 is equal to 3.031 inches, is less than to 3.450 inches, use A is equal to 3.031 inches. B prime is equal to B minus D over 2, or 2.425 minus 7 over 8 over 2 is equal to 1.988 inches. A prime is equal to A plus D over 2 is equal to 3.031 plus 7 over 8 over 2 is equal to 3.469. D prime is equal to D plus 1 over 8. 7 over 8 plus 1 over 8 is equal to 1 inch. Elongation is equal to 1 minus d prime over p is equal to 1 minus 1 over 4 is equal to 0.75. The bolt cross-sectional area will also be needed in subsequent calculations. Area of the bolt is equal to pi times 7 over 8 squared divided by 4 is equal to 0.6013 square inches. Using LRFD solution, the design strength of 1 bolt is B is equal to Phi times Rn is equal to 0.75 times 90 times 0.6013 is equal to 40.59 kips. The total factored load is 1.2 DL plus 1.6 LL is equal to 1.2 times 20 plus 1.660 is equal to 120 kips. And the number of bolts required is 120 divided 40.59 is equal to 2.96. A minimum of 4 bolts will be needed to maintain symmetry. So try 4 bolts. The factor external load per bolt, excluding prime force, is T is equal to 120 over 4 or equal to 30 kips. P is equal to 8 over 2 is equal to 4 inches. 2B is equals to 4.85 inches or greater than by 4. So use P is equal to 4 inches. Compute alpha. B over T minus 1 is equal to 40.59 over 30 minus 1 is equal to 0.353. From equation 7.15, alpha is equal to 0.353 times 3.469 divided by 1.988 divided by 0.75 times 1 minus 0.353 times 3.469 over 1.988 or equal to 2.139. Because alpha is greater than 1, use alpha is equal to 1. From equation 7.18, required TF is equal to square root of 4 times 30 times 1.988 divided by 0.90 times 4 times 65 times 1 plus 0.25 times 1 or equal to 0.763 inches less than to 1.04 inches. Okay. Both the number of bolts selected and the flange thickness are adequate and no further computations are required. To illustrate the procedure, however, we compute the prying force using equations 7.20 and 7.14. From equation 7.20, alpha is equal to 1 over 0.75 times 4 times 30 times 1.988 divided by 0.90 times 4 times 1.04 squared times 65 minus 1 or equal to negative 0.07657. Since alpha must be between 0 and 1, inclusive, use alpha is equal to 0. From equation 7.14, the total bolt force including prying is BC is equal to 30 times 1 plus 0.75 times 0 over 1 plus 0.75 times 0 times 1.988 over 3.469 is equal to 30 kips. The prying force is Q is equal to VC times T is equal to 30 minus 30 is equal to 0. This indicates that this section is not flexible enough to produce prying action. A WT 10.5 by 66 is satisfactory. Use for 7/8-inch diameter group A bolts. For A is D, the allowable tensile strength of one bolt is B is equal to Rn over omega or equal to 27.06 kips. The total applied load is D plus L is equal to 20 plus 60 is equal to 80 kips. The number of volts required is 80 divided by 27.06 is equal to 2.96. A minimum of 4 volts will be needed to maintain symmetry, so try 4 volts. The external load per volt, excluding prime force, is T is equal to 80 divided by 4 is equal to 20 kips. Compute alpha. B over T minus 1 is equal to 0.353. Alpha is equal to B over T minus 1 times A prime times over B prime divided by elongation times 1 minus B over T minus 1 times A prime over B prime, or equal to 2.139. Since absolute of alpha is greater than 1, used 1. From equation 7.19, required TF is equal to square root of omega for TB prime over PFU times 1 plus elongation times alpha, or equal to 0.936 inches less than 1.04. So, okay. Determine the prying force. From equation 7.21, alpha is equal to 1 over 0.75 times 1.67 times 4 times 20 times 1.988 over 4 times 1.04 squared times 65 minus 1, or equal to negative 0.07406. Since alpha must be between 0 and 1 inclusive, use alpha is equal to 0. BC is equal to T times 1 plus elongation times alpha over 1 plus elongation times alpha times B prime over A prime, or equal to 20 kips. The prying force is Q is equal to VC minus T is equal to 20 minus 20, or equal to 0 kips. This indicates that the T section is not flexible enough to produce prying action. A WT 10.05 by 66 is satisfactory. Used for 7 8-inch diameter group T bolts. If the flange thickness in example 7.9 had proved to be inadequate, the alternatives would include trying a larger T-shape or using more bolts to reduce T, the external load per bolt.
Simple connections. Topic outline. Welded connections. And fillet welds. Flow chart. First is introduction and next is the type of welded connection. Structural welding is a process whereby the parts to be connected are heated and fused, with supplementary molten metal added to the joint. For example, the tension member lap joint shown in the figure. It can be constructed by welding across the ends of both connected parts. A special coating on the electrode vaporizes and forms a protective gaseous shield, preventing the molten weld metal from oxidizing before it solidifies. The electrode is moved across the joint, and a weld bead is deposited, its size depending on the rate of travel of the electrode. As the weld cools, impurities rise to the surface, forming a coating called slag that must be removed before the member is painted or another pass is made with the electrode. Examples of fillet weld. Examples of groove weld. Topic outline. Welded connections and fillet welds. For the formulas to be used is for a given length of weld L subjected to a load of P, the critical shearing stress is Fv equals to P over 0.707 WL, where W is the weld size. If the weld ultimate shearing stress FNW is used in this equation, the nominal load capacity of the weld can be written as Rn is equals to 0.707 WLFNW. Electrodes should be selected to match the base metal. For the commonly used grades of steel, only 2 electrodes need to be considered. Use E70XX electrodes with steels that have a yield stress less than 60 ksi. Use E80XX electrodes with steels that have a yield stress of 60 ksi or 65 ksi. The ultimate shearing stress FNW in a fillet weld is 0.6 times the tensile strength of the weld metal, denoted FEXX. The nominal stress is therefore FNW is equals to 0.60 FEXX. For simple, that is concentrically loaded, welded connections with both longitudinal and transverse welds, AISC J2.4c specifies that the larger nominal strength from the following two options be used. First is use the basic weld strength FNW is equals to 0.6 F. For both the longitudinal and the transverse welds, use Rn is equals to RNWL plus RNWT given AISC equation G2-10A. Second, use the 50% increase for the transverse weld, but reduce the basic strength by 15% for the longitudinal weld. That is, use FNW is equals to 0.85 times 0.6 FEXX for the longitudinal welds, and FNW is equals to 1.5 times 0.6 FEXX. For the transverse welds, use Rn is equals to 0.85 RNW plus 1.5 RNWT given AISC equation J2-10B. For LRFD, the design strength of a fillet weld is phi Rn, where phi is equals to 0.75, and for ASD, the allowable strength is Rn over omega, where omega is equals to 2, and for yielding, the nominal strength is Rn is equals to 0.6 Fy AGV, given AISC equation J4-3. For LRFD, phi is equals to 1, and for ASD, omega is equals to 1.50. For rupture, the nominal strength is Rn is equals to 0.6 Fu ANV, given AISC equation J4-4. For LRFD, phi is equals to 0.75, and for ASD, phi is equals to 2. And for LRFD equations, weld shear strength is phi Rn is equals to 0.75 times the quantity of 0.707 WL FNW. For the base metal shear strength, phi Rn is equals to min times 1 times the quantity of 0.6 FYTL for the shear yielding strength, and for the shear rupture strength, 0.75 times 0.6 times FUTL. For weld shear strength, PRN is equals to 0.75 times the quantity of 0.707 WFNW for a 1-inch length. For base metal shear strength, PRN is equals to min times 1 times 0.6 FYT for shear yield strength, and for shear rupture strength, min times 0.75 times the quantity of 0.6 FUT, both is for a 1-inch length. For ASD equations, weld shear strength is Rn over omega is equals to min times 0.6 FYTL over 1.50 for shear yield strength. For shear rupture strength is min times 0.6 FUTL over 2. For base metal shear strength, Rn over omega is equals to minimum times the quantity of 0.6 FYTL over 1.50. For shear rupture strength, 0.6 FUTL over 2. Weld shear strength, Rn over omega is equals to 0.707 WFNW over 2 for a 1-inch length. For the base metal shear strength, Rn over omega is equals to mean times the quantity of 0.6 FYT over 1.50 for shear yield strength. For shear rupture strength, mean times the quantity of 0.6 FUT over 2. Both is for a 1-inch length. For the procedure, for the investigation, first is solve for Rn. Second, for LRFD and ASD solution, solve for the design strength, the allowable shear yield strength, and the allowable shear rupture strength. Then, the smallest value will be multiplied by the thickness phi Rn. Third, the phi Rn that controls will be the answer. Procedure for the designing, first is check for the minimum size. Second, for LRFD and ASD solution, solve for the design strength, the allowable shear yield strength, and the allowable shear rupture strength. Solve for the factored load, solve for the required length, solve for the minimum length, and the minimum length must be less than the required length. Second, use the 50% increase for the transverse weld, but reduce the basic strength by 15% for the longitudinal weld. That is, use FNW is equals to 0.85 times 0.6 FEXX for the longitudinal welds, and FNW is equals to 1.5 times 0.6. Solution. Because the welds are placed symmetrically about the axis of the member, this connection qualifies as a simple connection, and there is no additional load due to the eccentricity, since both weld segments are parallel to the applied load. Angle is equals to 0 degrees, and the basic strength of the weld is FNW is equals to 0.60 FEXX. The nominal load capacity per inch of weld is, by the formula Rn, and by substituting the value, we get 5.568 kips over inch. For LRFD solution, the design strength of the weld is phi Rn is equals to 0.75 times 5.568. We get 4.176 kips over inch. Next is check the base metal shear. For the phi Rn, by substituting the value, we get 5.4 kips over inch. For the shear rupture strength is phi Rn, by substituting, we get 6.525 kips over inch. The base metal shear strength is therefore 5.4 kips over inch, and the weld shear strength controls. For the connection, phi Rn is equals to 4.176 kips over inch times the quantity of 4 plus 4 is because of the thickness is equals 33.4 kips. For ASD solution, the allowable strength of the weld is Rn over omega, and by substituting the value, 2.784 kips over inch. Check the base metal shear. Since both components are of the same type of steel, the smaller thickness will control. The shear yield strength is Rn over omega, and by substituting the value, we get 3.6 kips over inch. The shear rupture strength is Rn over omega, and if we substitute the value, we get 4.35 kips over inch. The base metal shear strength is therefore 3.6 kips over inch. The weld shear strength controls. For the connection, Rn over omega is equals to 2.784 kips over inch times the quantity of 4 plus 4 inch. We get 22.3 kips. So the answer is 22.3 kips. It is our allowable strength of the weld. For our next example, a plate 1/2 by 4 of A36 steel is used as a tension member to carry a service load of 6 kips and a service load of 18 kips. It is to be attached to a 3/8-inch gusset plate. As shown in the figure, design a welded connection. For the solution, given by the AISC table J2.4, the minimum size would be 3/16 inch. For LRFFD solution, try a 3/16 inch fillet weld using E70XX electrodes. The design strength per inch is 1.392D is equals to 4.176 kips/inch. For the shear yield strength of the base metal is 0.6 FYT. Substituting the value, we get 8.1 kips/inch. Structural welding is a process whereby the parts to be connected are heated and fused, with supplementary molten metal added to the joint. For example, the tension member lap joint shown in the figure. It can be constructed by welding across the ends of both connected parts. A special coating on the electrode vaporizes and forms a protective gaseous shield, preventing the molten weld metal from oxidizing before it solidifies. The electrode is moved across the joint, and a weld bead is deposited, its size depending on the rate of travel of the electrode. As the weld cools, impurities rise to the surface, forming a coating called slag that must be removed before the member is painted or another pass is made with the electrode. For the answer, use a 3/16-inch fillet weld with E70XX electrodes with a total length of 9 inches as shown in figure. For ASD solution, try a 3/16-inch fillet weld using E70XX electrodes. The allowable strength per inch is 0.9279D, and by substituting the value, we get 2.784 kips/inch. And the allowable shear yield strength of the base metal is 0.4 FYT, which is by substituting the value, we get 5.4 kips/inch. And the allowable shear rupture strength of the base metal is 0.3 FUT. By substituting, we get 6.525 kips/inch. The weld strength of 2.784 kips/inch governs. The load to be resisted is PA is equals to D plus L, which is 24 kips, and the required length 24/2.784 is equals to 8.62 inch. And for the minimum length, 4W is equals to 0.75 inches, which is 0.75 is less than 8.62 inch, which is okay. Use two 4.5-inch long side welds for a total length of 2 times 4.5, which is 9 inch. For this type of connection, the length of the side welds must be at least equal to the transverse distance between them, or 4 inches in this case. The provided length of 4.5 inches will therefore be adequate. For the answer, use a 3/16-inch fillet weld with E70XX electrodes with a total length of 9 inches as shown in figure. Simple connection.